Okay, this is our chemistry video. Key point, sample temperature, 25 degrees Celsius, 77 degrees Fahrenheit. This is critical. This is the main thing to remember this whole thing. Any sample lab work, you have to maintain this. Even though they do have RTDs in the probes to compensate for temperature. The pH of water at 0 degrees Celsius is 7.47 pH. At 25 degrees Celsius, it's a 7 pH. And at 100 degrees Celsius, 212, it is 6.14 pH. Same water. Shows how the temperature affects the pH. pH, the meaning of the letters is really unknown. It's assumed to mean potential hydrogen. Nobody's really quite sure what he meant when he picked these two. But for all practical purposes, it's called potential hydrogen. It's a negative logarithm of the hydronium ions, H3O, to the base in mole liters. pH of 7 has equal amounts of hydroxide and hydrogen ions. pH is just to measure basically the hydrogen ions. All a pH meter is doing is measuring your hydrogen ions. A pH meter is strictly a voltmeter. You have two probes. You have a reference electrode, and you have the measuring electrode. The measuring electrode's in a separate solution down here. As this goes into a pH solution, it has a special glass. It has different metal ions in the glass, and it forms like a hydrated layer of water on both sides. That's why these probes have to be kept moist. We have an RTD that measures the temperature. That'll compensate temperature to the pH. You have a measurement here that measures the potential on this side of the glass. In order to complete the circuit, it needs to have a small junction that leaks a small amount of the potassium chloride solution out. It's like a 7 pH. This provides a return path for the current, so it can measure electrical potential across the glass, which will tell you the amount of hydrogen ion concentrations. So this is a pH of 7. If this goes above, it'll change the voltage, and if it goes below, it'll change the voltage. This kind of shows the calibration slope line. This pH probe, it has 59 millivolts per pH unit. So at 10 pH, it'd be 177 millivolts. At 7 pH, it's 0 millivolts. So this is your calibration slope line. When you first get a probe, or every so often, you use a 2-point buffer calibration. You can use 4 and 7, 7, 10. Nowadays they really don't care as long as they're a couple pH units apart. 4 to 10 is good. You get your slope line established. Then you do a standardization. You'll take a real accurate lab pH meter, check the solution, and compare it to this. Like if this is reading 7.5 and your bench shows 7.3, you can change that on your meter so this will read 7.3. It doesn't change the slope line, but it takes care of any variations in your sensor meter reading. This type of probe, you have to fill solution, you have to add solution every so often, maintain the level, because it does leak out small amounts down here. There's a lot more to these. Are really pretty complicated, but a big thing, you have to keep them moist. They don't like high temperature, and you do need to check the calibration routinely on these. Cation conductivity. Basically, you have a cation column. It takes out all the positive ions. Orange shows exhausted. Brown's kind of the color of the resin. It's a color change resin, which is nice. Here's your little conductivity cell. Basically, you remove water treatment chemicals. A lot of times using ammonia and positive ions. It amplifies contaminants, ions, the native ions such as chlorides, sulfites, and bicarbonates. It'll increase its sensitivity to low contaminant levels. Basically, you're worried about chlorides, sulfites, bicarbonates. Chlorides, sulfites can cause damage to turbine blading, intergranular corrosion stress cracking. So you want these very, very low. It will not show silica as that's a different ion. Conductivity. The big thing with this is the change per degree Celsius. With pH, it had a big change. Conductivity is even more. Acids can be 1 to 1.6% change per degree Celsius. Bases 1.8 to 2.2% change per degree Celsius. Salts 2.2 to 3% per degree Celsius. That's why you have RTDs on this to try and compensate for temperature. And that's why you really need to maintain the 25 degree in a chemistry lab to get as accurate as you can. Even water has a change. Specific conductivity, there's two plates, 1 centimeter square, 1 centimeter apart, and it measures the electrical conductance across these plates. Pure water has very, very low conductance, and the more salts in it, the higher the conductance goes. It measures in mhos, which is ohm spelled backwards. Conductivity meters, they use a cell constant number. They may be built different than this, but it's been compensated for. They may have probes in here or whatever, but this is what they reference back to. There's an AC signal that goes across these. If it's DC, you'd probably have electrolysis. These are like a 1 to 3 kilohertz signal across your AC. A mho is too large of a unit for measurement for water treatment, so we use micromhos or microsiemens. You'll see both of these. Microsiemens is the metric, and they're both fairly similar. You can be used interchangeably. Big thing is inferred pH. This is what a lot of analyzers will use. You can use the conductivity to give a pH reading if you know the chemical in the water, or basically if the chemistry is known. If you're using ammonia in your system, you have a conductivity of 15 micromhos, and you know your pH. Conductivity goes up to 20-25 micromhos. pH stays the same. You can pretty much guarantee you have a pH meter problem. This is really a handy guide to use because conductivity probes are very durable. They don't require a lot of calibration, whereas a pH meter is fairly sensitive. So this is the good thing to track your pH meters with. If you're using the same chemistry in the plant, you should know your conductivity based on pH. You can double check your pH that way. Dissolved oxygen probes, they're kind of amazing. They'll read parts per billion. Actually, they'll go down below a part per billion, which very small amount of oxygen in the water. Basically, they have a gas permeable membrane down here. They pitch tight over a cathode. There's a silver anode, and this is full of a electrolytic solution inside. O2 diffuses through the membrane to the cathode. There's a polarizing voltage applied to the cathode, and that converts the O2 to hydrogen hydroxide ions, and this reaction produces a small current. These have really small zero current when you set these up, and that has to be compensated for. To calibrate these, you put them in a solution of sodium sulfite, try and get the O2 down to 0, and it takes about 5 hours for it actually to read. Then you can zero the meter, then you take it out, expose it to air, and they'll give you the high range. There's a fill plug. You need to change the solution in these every 6 months. A little hole here to compress the bladder and try and get all the air out. Use a blunt object in here so you don't wreck the bladder. The membrane changes really easy. That's part of your rebuild on them. They don't have a kind of a shorter shelf life, but they work very well if you set them up. Most power plants, you'll see it down underneath one. You think they're not working, all of a sudden you have a big spike in O2, something happens. So they are handy for checking for dissolved oxygen, air leakage, and other problems. Okay, it's kind of the operation part of this. As operators, this would be great for a qual test question or on a test. Reality, all you gotta know is low pH is acid, this part is basic. You want to keep your boiler on this end of the scale. pH probes are really sensitive. They have to be kept moist. There's a hydrated layer in the glass around the outside of them. So you should always keep them in a storage solution. If you shut down the lab, keep these things in water. A lot of times there'll be a little vessel where the water comes in, drains out, try and maintain level. If you shut down, put them in some kind of storage solution. A lot of times you use the bench pH probe to calibrate your field instrumentation. You need to make sure this is very accurate before you go changing the plant analyzers. If you're running in a normal power plant, it'll be about 9 pH, somewhere up here. Put this in a 10 pH solution. Make sure you're reading a 10. Your storage solution should usually be like a 6.3. You can use that for 1 point. Use the 10. If you're down here, use a 4. Or if you want to, you can use 2 points just to verify it. But you'll find most time if you do a 10 pH and you're doing power plant chemistry, it'll get you very close. The reason you have to calibrate your field instrumentation, they do change every so often. It could be the transmitter issues or something changed on it. These are run pretty close. You got to be careful too, because the water flow, your sample point here, it may take longer for it to get back to the transmitter. So you might be changing it when you don't need to. So you need to try and get your sample really close to where the analyzer is. If it's a ways away, this might be reading 7.7. You think it should be reading 7.5, whereas your sample is quicker or slower than the other one, and you'll be changing it and you'll be wrong. Standardization, like I said, you may have to do this occasionally. Just try to get your analyzers correct in the field. You'll get one shift change one way, and the next shift changes the other way. I can see a lot of those problems going on. So you need to be very careful and get this as accurate as you can before you go changing stuff in the field. That's where inferred pH is really handy. If you know the conductivity, you know where the pH should be. Somebody changes this, and the conductivity is where it should be for the pH, and you know they made a mistake on that. Cat columns, have to change them every so often. This part's exhausted. This is the resin. Sometimes you can recharge these yourself if you have a demineralizer, but mostly it's just disposable resin. You need to keep it water flowing through conductivity cells. pH probes like to be in water that's not moving. A lot of times in the plant, there's a little bit of flow going through the sample containers. Conductivity probes need a little bit of water flow through them to read correctly. Dissolved oxygen. You have to change the membrane, change the solution inside here. Every 4 months or so. There's a little hole here to compress the bladder and try and work the air out after you fill it with this fill plug. Use a blunt object, you could damage the bladder inside of it. These are the same as a chlorine probe. They work similar, have a membrane, the solution inside. Have to read the manual on these to do it. They're kind of a trick. To zero these, you have to have a zero oxygen solution. Use sodium sulfite and water. And that's going to be your zero oxygen. If you're running down into less than a ppb of oxygen, your zero has to be zero. Have to be really careful how you get the zero calibration. And the upper range is just exposed to air. It can take 5 hours in the solution or more to get the calibrated down to the ppb accuracy. And a new probe may have to sit 24 hours. The big thing with these, you just have to have maintenance on all this stuff. The pH probes, they're a short-lived deal. You get about a year out of them. They can run longer than a year, as long as you check the slope's okay and you're getting your 59 millivolts at pH. It's okay to keep using them. They don't like high temperature. They don't like to be dried out. And in pure water, I say you're going to have problems measuring just because of the lack of current flow back. Cold temperature water, it can be very hard to get a pH of. You'll be seeing, you'll bring a pH sample back to the lab, warm it up, and it's going to be way different than this. You can standardize it. I mean, even with the RTDs and these things, it's critical to have the 25-degree sample temperature, but they do work fine in the field.
Yeah.
Here's some different probes. This is a pH probe. I can see on the end of it, you have the center glass bulb in the middle. That's your measuring. References around the outside of it, that white part. The silver pin's the RTD, resistance temperature device. One big thing on these, always put down the date when you change them out. That's important, that way you know how long they've been running. So you can see there's a lot of pin connections on the end of these. I got RTD and you got your wires coming off the two probes. This is an oxygen sensor. So you can see you have your fill plug here. That's where you had the fluid at, electrolyte, and drain it. Over here there's a little hole. You can use something to blunt object to exercise the bladder and get the air out. On the end of it, you can see the electrode and then your membrane. membrane distance screws. That's your cathode, that gold part in the center. There's three little holes. Part of electrical conductivity goes through those. Here's your membrane. These they get coated up with debris in the water, and they need to be changed every so often. Chlorine probes, same style. Big thing is to get all the air out of the electrolyte when you redo these. This is a conductivity probe. It's pretty hard to see the inside of it. There's two plates. There's also an RTD in this to measure the temperature. These need to have flow through them, and they can't be dry. So this outlet tube here will loop down, come back up, so there's always water above it. They need water flow through them, and they need to be completely submerged. These don't really require much maintenance. That's why they're so good for doing inferred pH with. These can be used for cat columns and also straight conductivity. We call straight, it's also called specific conductivity. That is just conductivity of the water. Cat conductivity is going to a cat column. Sometimes the cat columns too, you'll degasify, go through a heater and take all the carbon dioxide out of the gas out of the water. That way it gives you a little bit more accurate cat conductivity reading.